Okay, now we continue with subchapter 5.3, which is control and instrumentation symbols. Okay, for basic control symbol, as you all know that PNID use simplified symbols, and for each instrumentation they use a circle to represent it. Okay, PNID also follow a international standard symbol, which is instrumentation system and automation. In other words, we call it as ISE. Okay, in PNID also we have a tag number. That tag number are letters and number placed within or near the instrument to identify type and the function of the device. Okay, basic symbol for the control and instrumentation is a control valve and also actuator. Most of control valves are actuated by pneumatic signal using instrument air. What is meant by this statement is, okay, this is a control valve. So to operate, the control valve is operated by opening and closing the control rack. So in order to open and closing the control, they use the air. So that's why we have to use the pneumatic signal when the control valve is operated by air. But in other case, the control valve also is operated by power supply. That means the opening and closing of that valve is supplied by the electrical power. Okay. Pneumatic actuators are preferred in some situations in which electronic controller might cause a process hazard or electric power is not available or reliable. Okay, this is a few type of instrument line. Okay, basically the solid line that we normally use inside the PNID, it is referring to the process line. Okay, basically like this. Okay, if your control valve using the instrument air like what I mentioned before, you need to use pneumatic signal. If your control valve using the electrical power, so you need to use the electric signal. Okay, we have another type of instrument line which is electric binary on off signal and also internal system link. So all of these instrument line you have to consider inside your PNID. Okay, this is the letter code for instrument symbol. Okay, I take one example which is level. Okay, normally we take a first letter which is level L. So if the level is combining with the indicating, that's mean level indicator, it become Li. I stand for indicator. Okay, if for example like the controller type is recording, means level recording controller, so we have to denote it as a LRC. For level indicating controller, LIC, but normally we use LIC in our control system because it integrate in one circuit with the indicator. So if you use LIC, you did not need to use the LI before the LIC. Okay. Other letter code is transmitter for the level LT, level transmitter. Okay, now I move to instrument location. We have two types of location, which is locally mounted and also main panel. For the locally mounted, means that the controller itself and display located up of the plant, near to the sensing instrument. For the main panel, the controller located on a panel in a control room. Except on a small plant, most controller would be mounted in control room. Okay. basically we have three types of symbol that denote the location of instrument itself. Okay, if you guys notice that if the symbol is don't have any line inside the circle, the instrument is mounted in the field near the process close to the operator. But if the instrument symbol with a solid line, the instrument is mounted in the control room, accessible to the operator. For the symbol, the instrument symbol with a dash line, it means that the instrument is mounted out of sight, not accessible to the operator. So this one also you need to consider in your P&ID. Okay, now I give one example of typical control loop. Okay, this is a pressure control system. Okay, we can see here the transmitter is connected with the pipeline. So this transmitter will measure the pressure along this pipeline and will send the information to the pressure indicator controller. Okay, basically after the transmitter we have a alarm. This is the pressure alarm high, pressure alarm low. So this alarm to alert the operator if the pressure increase or decrease very high. So okay, after the information is sent to the pressure indicating controller, so the controller will send the information to the control valve. So the control valve will perform the corrective action based on the decision made by the PNIC. So this one you can see here the dash line. It means that this control valve is operated by power supply. So in the case of the if the failure happen inside the plant, this valve will directly close. So the gases with the high pressure will not simply go out when there is a failure inside the plant. Okay, now I'm moving to the subchapter 5.4, which is type of control. Okay, for the control system, we have two ways of controlling. First is feedback, second is feed forward. Normally in industry we use feedback for our primary control system, but feed forward is sometimes added to improve the performance of the feedback system. Okay, what is feedback control? Okay, a feedback loop measure a process variable or control variable and send the measurement to the controller for comparison to set point. Okay, this one I will show the figure in detail so that you can understand more after this, but here I will explain what is the detail about the feedback control. Okay, the advantage of this feedback control is it is simple because using a single transmitter, and this control scheme does not consider any other variable, for example like disturbance in the process. The advantage of this feedback control, it can directly control the desired process variable. Okay. This is the diagram for the feedback control. Okay, we can see here the feedback control will measure the process variable or control variable inside, and then it will send the information to the controller, and this controller will make the comparison between the process variable inside here with the set point and make a correction based on that and send the information to the valve to take an action. Okay, now I move to the feed forward control. Okay, the objective of feed forward control is different as compared to feedback control. Okay, feed forward control is used to measure the disturbance and compensate them before the control variable deviate from the set point. Okay, as compared to the feedback just now, for the feedback we do not consider any other variables such as disturbance. The controller just measure the process variable or control variable and make correction based on the deviation of process variable from the set point. For the feed forward control, we measure the disturbance and we compensate the disturbance, means we cancel out the disturbance first so that the system become ideal, so that there is no any other process variable that can deviate the control variable from the set point. If this feedforward control apply correctly, the control variable deviation would be minimum. Okay, this is the diagram for feed-forward control. Okay, we can see here the feed-forward control do not measure the process variable inside this column, but it measures the disturbance, which is the fluid in, and the controller make a correction based on the measured disturbance here and send the information to the controller and to take an action so that the disturbance here can be cancelled out. Okay. Now I want to compare between the feedback and feed forward. Okay, feedback control, the advantage is corrective action occurs regardless to the source and type of disturbance. That means it do not consider the type of disturbance. And the other advantage is it requires little knowledge about the process. For example, a process model is not necessary because we only consider the control variable. Okay, the disadvantage of this feedback control is no corrective action until a deviation in a control variable occurs. So it will start to do a correction after the process variable deviate from the set point. Mean the output itself, if the output deviate, then the controller will do a corrective action. The other disadvantage is incapable of correcting a deviation from set point at the time of its detection. That means if the deviation occur at the input, this feedback controller cannot cater the problem because it's only do a corrective action at the process variable, which is at the output. If the output deviate from that point, then it will do a corrective action. Theoretically, this feedback control not capable of achieving a perfect control. And the other disadvantage is for frequent and severe disturbances, process may not settle up. So for the process with a severe disturbance, it is better to use a feed-forward control. Okay, now I move to feed-forward control. The advantage of this feed-forward control, it takes corrective action before the process is upset. That means it takes at the starting point of the process, it cancels out all the disturbance first. Then the process can run smoothly. Okay, theoretically, this feed-forward capable for perfect control, and it does not affect system stability. The disadvantage for this feed-forward control, disturbance must be measured. When we add additional sensor to measure the disturbances, so it will cause the operating cost become higher. The other disadvantage is the feed-forward control require more knowledge of the process to be controlled. We need to know every parameter, every input variable that can cause the deviation of this system. So to know this, to know the every variable and parameter, we need to do a detailed study. Okay, next I move to the cascade control. Okay, it is quite different as compared to feedback and feed forward. Basically, feedback and feed forward control is a single loop control, but this cascade control, we have a double loop control. Okay, the loop consists of primary loop and also secondary loop. So the function for the primary loop is to monitor the control variable and use deviation from its set point to provide an output to the secondary loop. Okay, later on I will show the figure on this cascade control so that you can understand more. Okay, for the secondary loop, receive its set point from this primary loop and control the reference variable accordingly. That means the output from the controller from this primary loop is sent to the secondary loop, and then the secondary loop controller will do a corrective action based on the data given by the primary loop. Distinguishes features of cascade control: two control loop with a single valve. Okay. Output signal at the master controller is the set point for the slave control. Okay, master controller is a primary loop. Meanwhile, for the slave controller is a secondary loop. The slave control loop is nested inside the master loop. Okay. After this, I will show the figure. What is slave? What is the master? Okay. Master or primary controller, the input to this controller is the measured value of the variable to be controlled. Okay, like feedback control, the input to this control is measured value. Means we measure directly from the process, and then from the sensor, the data is sent from the sensor to the controller, the master control. Then the set point is applied by the operator. It passes its output signal to the inner control loop. So after the output will be sent to the slave controller. So the slave controller will measure a second variable whose value affect the control variable. Okay, the set point is applied by the output from the outer loop. Means the set point is based on this master loop. Okay. Its output signal is used as a signal to the manipulated variable. So this output signal will be sent to the control valve, and the control valve will be adjusted based on the corrective action given by this slave controller. Okay, here we can see the block diagram for the cascade control. Okay, here we can see the process, our process. So the control variable is here, for example like level. Okay, the control variable is level. So the set point, for example, level at 5M. Okay, the sensor will measure the level from this process and send the data to the primary controller. So set point is input to this primary controller, which is I mentioned is 5 meter. So after do a comparison between the set point and also the measured control variable, the primary controller will do a corrective action and send the data to the secondary controller. So secondary controller here normally is flow controller. So this is a flow control. So the output from the primary controller will be the input for the secondary controller. But still, secondary controller have to measure the parameter in the process. So based on that parameter, it will do secondary correction and will send the information back to the final control element, and final control element will do the action based on the output from this secondary controller. If there is any deviation occur here, it will also do a correction and send the data to the control element. So this cascade control will cater any deviation on control variable and also disturbance variable. Okay, now I move to the case study for the cascade control. Okay, the application is on the reactor temperature control. Okay, the main objective of this controller is to keep temperature T2 here at 8 set points. So CV here is temperature T2. Okay, the function of this primary temperature control is to detect and eliminate any changes in T1. These changes actually will cause the deviation of this control variable. So that's why this primary controller will detect and eliminate any changes of this one, so that the deviation of the control variable will be minimized. Okay, the secondary control loop will detect the changes in the temperature of the cooling water. Actually, this reactor consists of the jacket, and this jacket, there is a feed of cooling water. The function of this jacket is to cool down the reactor. So the secondary control loop, the function is to detect changes in the temperature of the cooling water. It will adjust the flow accordingly before the effects are detected by the primary control loop. That means why we have to detect the changes inside the cooling water. Sometimes this one will cause the temperature inside the reactor, the control variable itself T2, deviate from the set point. So that's why we also need to cater the changes occurred inside this cooling water. So that's why we have two control loop. Firstly is to cater this T1. Secondly is to cater the changes of the cooling water. So if there is no second controller, the effect of this cooling water will take a long time to materialize and eliminated. Then it will cause the control variable to deviate more, and it take for the system to achieve set point longer. Okay, now I move to distillation bottom temperature control example. Okay, the main control objective here is to control the bottom temperature of distillation, and the control variable would be the bottom temperature. Okay, the manipulated would be, okay, we can see where is the valve is located at the steam flow rate, right? Okay, so now I will explain the working principle of the cascade control. Okay, the primary controller here, also known as a master control, will detect any changes or any deviation of control variable from the set point. Okay, normally the deviation is caused by changes in composition, pressure, and etc. Okay, if the temperature inside here is low, the primary controller will do a comparison and will send the data to the secondary control loop, and will ask the secondary control loop to supply more steam so that the temperature inside here will be increased and achieving the set point for the primary control loop. So here the primary control loop will send a new set point that need to achieve by the secondary control loop. Okay, the secondary control loop, and also known as a slave control, will detect the changes in the steam flow rate. So now it will get two data, which is from the primary and also from the sensor at the steam flow rate, and it will do a corrective action based on the both data, and will send the data to the final control element, and final control element will do the action to cater the mentioned problem just now. Okay, bear in your mind why we normally use a flow rate, flow level as a secondary controller, because one main criteria to select the secondary controller is it should have a fast response. Normally, flow level controller is a fast response control, as compared to the temperature is a slow response control. Okay, I'm moving forward. Okay, basically this is the example of the PFT for the example 2 just now. Okay, here we can see temperature control will get the signal from the temperature transmitter, and it will detect the temperature control variable here, the bottom temperature inside here, and then it will send the data to the flow control, and flow control will also measure the steam flow rate, and do a corrective action and send the data to the final control element. The final control element, the steam flow rate will be adjusted accordingly and will cause the temperature inside the column to increase or decrease achieved to its set point. Okay, I think that's it for the sample 2. Okay, actually we already cover all of chapter 5. I hope you guys can understand to what I explained before. Okay, please ask me if you have any question or any confusion. Thank you.